Hello Year 10, welcome back. This is week 2 of rates of reaction in chemistry, and this week we're going to be looking at collision theory and recapping a little bit on last week's work. So the first thing I need you to do is download this PDF, which is visible on your Google Classroom. You should also see a Google Doc, which you're now able to type your answers directly into. Some of you have asked questions about how you paste images into your work. In the top menu bar there is a button that says Insert, then you can click Drawing and click New Drawing if you need to insert an image. You can then copy and paste any images into that and it will insert it into your work. You can also draw things within that. So the first thing I want you to do this week is do some recap questions on what we studied last week. So if you could pause the video here, go over to your Google Doc, type your answers directly in for these questions. Okay then guys, right. So section 1, we're looking at why chemical reactions take place. Recap on last week, we have reactants and we have products in any chemical reaction. And if we were to look at this in terms of a particle model, here's my reactants A and B, and here's my product C. And in order for a reaction to take place, the reactant particles need to collide. Okay, so there's a key word there, collision. So we need a collision between those reactant particles in order for a reaction to take place. Now, in order for that collision to successfully result in a chemical reaction, in other words, form a product and use up those reactant particles, we say that the particles must have enough energy, okay? And that minimum energy that the particles need in order to react is called the activation energy. And I've given you a definition of activation energy here, the minimum energy to start a reaction. You've probably seen the term activation energy before, and this was applied to endothermic and exothermic reaction profiles that you studied in the energy changes chemistry unit last time. It's very important that your diagrams, when you draw these, are drawn exactly as I have drawn mine here. Okay, so I'm going to highlight some of the key features of these reaction profiles and teach you some little tricks about getting them right. Endothermic means it absorbs heat energy. Okay, so in endothermic reactions, where they absorb heat energy, the surroundings actually get colder, so the surrounding temperature decreases because it's having heat energy absorbed from it. Now it's actually the conversion of reactants to products that's absorbing that heat energy. So we can see that reactants start off with a lower energy, but the products have a higher energy here because energy has been absorbed. And we call this energy arrow here the energy transfer. And the energy transfer arrow in any reaction profile is always starting at the reactants and going up to the products. See how it starts on exactly the level of the reactants and finishes where the products are. You have to make sure you draw these arrows very accurately. Okay? Now this minimum energy to start the reaction is called the activation energy. And notice here how it always starts at the reactants and it touches the peak. Okay? Let's have a look at our exothermic reaction profile here. Well, exothermic reactions release heat energy to the surroundings. So the surrounding temperature is going to increase because it's had energy released to it. So we would measure a temperature increase for exothermic reactions. Again, my energy transfer always starts at the reactants and finishes at exactly the level of the products. Okay? And my activation energy always starts at the reactants and touches the peak. Reactants to peak, reactants to peak, reactants to product, reactants to product. So R to P, reactants to peak, reactants to product. As long as you follow that rule, you'll always get both endothermic and exothermic reaction profiles correct. Now let's link that activation energy now to this idea of a collision between reacting particles. So here what I've done is drawn some images to illustrate a successful versus an unsuccessful collision. A successful collision is one in which the reactant particles have energy equal to or above the activation energy. And this collision is successful because the collision results in the formation of a product. Here I have an unsuccessful collision. These reactant particles didn't have energy equal to or above the activation energy. They had energy below the activation energy. So therefore, when they collided, they didn't convert into products. They just bounced off of each other. So it is important that a collision occurs with reactant particles that have energy equal to or above the activation energy, so the collision is successful and forms products. Let's now have a look at why rates of reactions slow down over time. Last week I showed you some graphs and they all pretty much took this shape. And this shape followed a trend. The gradient was steep at the start of the reaction, so the rate was fast. The gradient then began to shallow, so the rate was slowing down. The gradient then reached 0, so the reaction had stopped. In this case, the reaction had stopped at 120 seconds. We can explain this using the idea of collisions. At the start of any chemical reaction, we have got lots of reactant particles because not many of them have been used up yet. So we can say at the start of a chemical reaction, the reactant particles are in a high concentration. If the reactant particles are in a high concentration, there's going to be a high frequency of collisions. We can't just say there's going to be more collisions, we need to say that there's going to be a high frequency of collisions. The word frequent must always go in front of the word collisions. So, start of the reaction, high frequency of collisions because there's a high concentration of reactant particles, which means our rate of reaction is fast. As the reaction proceeds, the rate of reaction begins to slow down. And this is because the frequency of collisions decreases. So there are less frequent collisions if a rate is slowing down. Why would there be less frequent collisions? Well, as the reaction proceeds, reactants are converted into products, and therefore we can argue that there's now a lower concentration of reactant particles as they're being used up. So this lower concentration of reactant particles as they've been used up results in less frequent collisions, which results in a slower rate of reaction. Finally, at the end of our reaction, where it's stopped, we could argue that all of our reactant particles have been used up, so there are no collisions, and this is why our rate of reaction has stopped. So, if you could pause the video here, have a look at your Google Doc and type your answers directly into it for these task questions that you see here, then come back to the video and we're going to move on to the next section. Okay, so let's have a look at our next section. We're now looking at factors which affect the rate of reaction. I said earlier that any factor which affects the frequency of collisions will affect the rate of reaction. So we talked about particles getting used up, lowering their concentration, which results in less frequent collisions. When we talk about collision frequency, we've always got to put the word frequent in front of the word collision and then say whether the frequency of collisions is more or less. So an examiner wouldn't accept more collisions gives you a faster rate of reaction, but they would accept more frequent collisions gives you a faster rate of reaction. So please do not be writing more or less collisions. Say more frequent collisions or less frequent collisions. So we've got 5 factors here that are going to affect the rate of reaction. The first is temperature, second is pressure, third is concentration, fourth is surface area, and the fifth is catalyst. Let's begin by looking at how temperature affects the rate of reaction. So we can say that the higher the temperature, the faster the rate of reaction. But we need to be able to explain this using collision theory. Here I've shown some particles at a high temperature, and I've drawn these long arrows here to represent them moving faster. The reason particles at a high temperature move faster is because they have more energy. Please never say they move more, you have to say they move faster, or they move at a faster speed. If they're moving faster, then there's going to be more frequent collisions. And more frequent collisions is going to result in a faster rate of reaction. But we could also argue that because they're at a higher temperature, they have more energy. So more of these reactant particles are going to have energy equal to or above the activation energy. So our frequency of successful collisions is also going to be higher. Here we've got some particles at a lower temperature. You can see I've drawn smaller arrows here to show that they're moving slower. The reason at lower temperatures they move slower is because they have less energy. Moving slower with less energy is going to mean that there's less frequent collisions. So if our frequency of collisions has decreased, then we're going to have a slower rate of reaction. We could also argue that where these particles have less energy, then there's going to be more of these particles with energy below the activation energy. So our success rate of collisions has also decreased. So there's less frequent successful collisions. Just to highlight here, temperature is the only factor that we will look at that affects the energy of particles. No other factor affects the energy of particles. Let's now have a look at how pressure affects the rate of reaction. A general rule, the higher the pressure, the faster the rate of reaction, and vice versa. This one's very straightforward to explain. We've got particles shown here at a high pressure and shown here at a low pressure. At high pressures, the particles are closer together. Makes sense? So there are more frequent collisions, so there's a faster rate of reaction. Notice how pressure does not affect energy in any way whatsoever. It's just about the distance between the particles. They're closer together at a high pressure. As we can see now, they're further apart at a lower pressure, so that's going to decrease our frequency of collisions. There are less frequent collisions, so we get a slower rate of reaction. Let's now have a look at concentration. The higher the concentration, the faster the rate of reaction, and vice versa. Now, if we look in the box for high concentration, you can see that there's lots of particles, whereas at a low concentration, there's fewer particles. But an examiner will not accept you stating that a high concentration is just more particles. They want you to express concentration in terms of particles per unit volume. So we need to say at a high concentration, there are more particles per unit volume. You have to add this per unit volume bit on the end. You will not get a mark for more particles. Okay? So if we've got more particles per unit volume, there's going to be more frequent collisions and a faster rate of reaction. Hopefully you're noticing a trend here. At a low concentration, there's going to be fewer particles per unit volume. So there's going to be less frequent collisions and a slower rate of reaction. Notice in each of these examples, I'm first talking about the particles, then I'm talking about the frequency of collisions, then I'm talking about the rate. Particles, collision frequency, rate. As long as you structure your answers in this format, you'll always get full marks. Let's now have a look at how surface area affects the rate of reaction, and this one's a little bit counterintuitive. In general, the higher the surface area, the faster the rate of reaction. But it's important to note that smaller particles have a larger surface area to volume ratio. So smaller particles, powders of substances, have a higher surface area. And that's because less of their matter is on the inside and more of it is actually on the outside as a proportion of its mass. In this reactant particle with the low surface area, which is larger, a lot of its actual matter is trapped on the inside of the particle. So it's not exposed on the outside, available to react. So we argue that smaller particles have a larger surface area to volume ratio. For example, powder. So with smaller particles, there's going to be more frequent collisions and a faster rate of reaction because they have a larger surface area to volume ratio. If we have a larger particle, for example, lumps, chips, or rocks of a substance, they've got a smaller surface area to volume ratio. So our frequency of collisions will be lower and we will get a slower rate of reaction. Now, catalysts do not affect the frequency of collisions, but catalysts do affect the success rate of collisions. And this is because catalysts lower the activation energy of a reaction. I've drawn here a reaction profile of a reaction, an exothermic reaction to be specific. I know it's exothermic because energy's been released and my products have less energy than my reactants. Now, normally the activation energy, reactants to peak, is quite large for this reaction. That's shown it without a catalyst. But we can see here, I've drawn an extra curve, and this is an alternate reaction pathway. So what a catalyst does is it provides an alternate reaction pathway with a lower activation energy. So therefore, in order for a collision to be successful, it needs less energy if you use a catalyst. So we can define a catalyst as a substance which speeds up the rate of a chemical reaction without being used up, and it works by providing an alternate reaction pathway with a lower activation energy. Now this is useful because it means that our reaction can be carried out at lower temperatures. And that's very useful for a chemical engineer because if they're carrying out a reaction at lower temperatures, they're going to put in less heat energy to make the reaction work, and that's going to save them money. So what I want you to do now, guys, is if you can pause the video here, directly answer these questions in Google Doc and then come back to the video to move on to the next section. Okay, so once you've answered those questions, what we're going to do now is look at poorly answered questions on collision theory, and this is really going to improve the way that we answer these questions, because I notice as a chemistry teacher a lot of students make these common mistakes which loses them marks, and we have to be very, very careful with our wording in these questions. So our first question says, explain why the reaction between magnesium and hydrochloric acid was faster at 50 degrees than it was at 20 degrees. So I've got a higher temperature here, so my rate of reaction should be faster at 50 than 20. Let's have a look at what the student's written. At 50 degrees, the particles have more energy, so they move more. This means there are more collisions and a faster rate of reaction. As I said earlier, it's not enough to just say the particles move more if they have more energy. You need to say they move faster. Secondly, this student has simply written more collisions. That would not be accepted. We would need to put the word frequent in front of the word collisions here, so we would need to say more frequent collisions. Let's have a look at this second example. Explain how using a higher concentration of hydrochloric acid will affect the rate of reaction. Let's have a look at what the student said. At a higher concentration there are more particles, therefore there's a faster rate of reaction because there are more collisions. The first error here is for saying that at a higher concentration there are more particles. They're not strictly speaking wrong, they've just not worded it specifically enough. They need to say there are more particles per unit volume if they're talking about a higher concentration. So always add this per unit volume bit on the end when we're talking about more particles. The second error they've made is the same as the last student. They've said there are more collisions. We must say there are more frequent collisions if we're justifying a faster rate of reaction. Let's have a look at this next example. Explain how increasing the pressure will affect the rate of reaction. The student's written this. At a higher pressure, the particles have more energy. Therefore, they collide more frequently and there's a faster rate of reaction. Okay, so this collide more frequently is good, but they've said the particles have more energy at a higher pressure. Remember, pressure does not affect the energy that the particles have. Only increasing the temperature affects the energy the particles have. So this should say that the particles are closer together if it's talking about pressure. Okay, number 4. Explain how using a catalyst affects the rate of reaction. Here's our incorrect student response. Using a catalyst increases the rate of reaction because the catalyst gives the particles more energy, meaning there are more frequent successful collisions. Catalysts don't give the particles any energy. All a catalyst does is lower the activation energy, the minimum energy those particles need in the first place. It's a little bit like if you're doing high jump and someone's lowered the bar. It doesn't affect the maximum height you can jump to, but you're more likely to jump over it because the bar is lower. So catalysts do not give the particles any energy. Only increasing the temperature affects the energy the particles have. Catalysts simply lower the activation energy needed for a collision to be successful by providing an alternate pathway for the reaction to take. So, if you can pause the video here, have a go at these task questions, write your answers directly into your Google Doc, and then come back for the next section. Okay, let's have a little look at more on catalysts now. So we've already said that a catalyst is a substance which speeds up the rate of a reaction without itself being used up, and it's able to do this by providing an alternate pathway for the reaction with a lower activation energy. But it's important to note that chemists don't actually write catalyst in the reaction equation as a reactant or product because they don't get used up. Okay, so I've got an example here. Here's the worded problem. Potassium iodide was added to hydrogen peroxide. The hydrogen peroxide decomposed to form oxygen and water. The decomposition reaction, so this whole reaction just described, was described using this equation. So here I've got the hydrogen peroxide as a reactant, and here I've got water as a product and oxygen as a product. But you'll notice that this potassium iodide substance is not featuring in either the reactants or the products. So if it's mentioned in the method, but it doesn't feature in the reactants or products, then it must be the catalyst. Now, we can give a reason for why it doesn't feature in the reaction equation. If we were to write this potassium iodide into the reaction equation, so just here, I've got exactly the same reaction equation as above. Look, there's the hydrogen peroxide, there's the water, there's the oxygen, but I've written the potassium iodide into it. Well, a key thing about a catalyst is it doesn't get used up. So it would be there in the reactants, but it would also be there in a product. So any of you guys know in math that you cancel out things that are either side of the equal sign. So if we do that here, cancel it out both sides, then we just end up with the original equation that we had here. Some things in biology are catalysts as well. And our key biological catalysts are enzymes. And the reason that they are catalysts is, again, they speed up the rate of a chemical reaction without being used up. But in this case, enzymes feature in biological systems, so inside the body, for example, or inside cells. Okay? So we can call enzymes biological catalysts. And a key example of an enzyme carrying out a chemical reaction is the breaking down of carbohydrates into sugars. You've probably seen this enzyme in biology, amylase. Amylase breaks down our carbohydrates, and you can see that we had our reactants here, the amylase and our carbohydrate, and then we've got our product here. It's broken down that carbohydrate into simple sugars, but the amylase is still there. Notice how it features both in the reactants and the products, so therefore it wasn't used up, therefore it's clearly a catalyst. Now, because catalysts lower the activation energy for reactions, as I said earlier, it means it lowers the temperature at which a reaction can take place. And that's very important inside biological systems. For example, the body, with an average temperature of about 37 degrees Celsius. Okay, so without having that catalyst there, that biological catalyst in the form of an enzyme to lower the activation energy of breaking down that carbohydrate, this reaction would not be able to proceed at 37 degrees Celsius. So it's important that the body has that enzyme there as a biological catalyst in order to lower the activation energy, meaning the reaction's feasible at a lower temperature. Okay, so if you want to pause the video here, have a go at these task questions, upload your answers directly into your Google Doc. Right then, so we've reached the end of week 2's tasks now. Please submit your answers by Friday at 3 o'clock. Thank you very much for watching this video, and I will see you in the next one.